Okay, this is an introduction to coal, and coal has been historically used primarily for power generation for a long time and is still a major source of energy production around the world. Coal is formed from plant matter, and as it decays and is in the earth, and the earth heats it, puts it under pressure, it undergoes a transformation process. So there's nominally 5 types of coal. They're called coal ranks. And early coal, young coal, is called peat. And then through heat and pressure, that gets converted to lignite. And then subbituminous coal, bituminous, and anthracite. And you can see pictures here. And as the process continues, you get more and more carbonization. Anthracite is made primarily of carbon, whereas peat will have other elements in it in higher concentrations. And anthracite is more rock-like, and peat, you can almost see the history of the material as plant matter. So let's see. So coal, peat, is coal precursor, and it's soft, organic, partly decayed plant matter. Lignite is brown coal, also called brown coal, has a relatively high moisture content and a relatively low heating value. And then subbituminous is dull black, used a lot for electricity. So is bituminous coal, has a high heating value. It's also used in steel production. And then anthracite is a hard, brittle, high carbon substance. And you can see here on this plot a comparison between the heating value on a moist mineral-free basis, so sometimes called a dry ash-free basis, DAF. Dry ash-free is how some of the organic content of the coal is characterized. And you can see here the percentage of fixed carbon. And so typically as you go towards more lignite, the heating value goes down, and as you go to these higher coals, the percentage of carbon increases. Coal is an extremely complicated composition. It doesn't really have a molecule per se. It's made up of chain-like structures that consist of aromatics and aliphatic components. These aromatics here are often grouped and then linked with smaller chains, and then they have side groups, and those side groups include oxygen species, nitrogen species. Sometimes there's sulfur that's incorporated into the fuel, and this is one reason why it's hard or nearly impossible to remove nitrogen or coal or sulfur from the coal, and so combustion and or post treatment is needed to deal with the nitrogen, and post gas cleanup is needed to treat the sulfur. As you heat this structure up, you get breakage along some of these bonds, and that results in volatilization of the coal. So when it gets hot, it releases gases, and those gases are what combust in the flames, and then leaving behind a carbon matrix that we call char, and that char then burns as a solid phase with oxygen diffusing to the solid to react and burn out the remainder of the fuel. And then any inorganic matter is what we call ash, and that comes out in the flue gas as an ash fume and is removed by particle collection devices. It can also stick to the walls and form slag. Sometimes this molecule is jokingly referred to as 1,2-dimethyl chicken wire. It's kind of fun. So here's a typical coal composition. This is a skyline coal. It's a bituminous coal in Utah. And there's 2 kinds of analyses that are referred to for coal. There's what's called the proximate analysis, and that's a characterization of the composition of the coal that is moisture, the composition of the coal that can be evolved as volatiles, and the composition as fixed carbon or char, and then ash. So it kind of gets the high level makes up this coal. Moisture, volatiles, fixed carbon, and ash is the proximate analysis. There's also what's called an ultimate analysis, and that's often done on a dry basis or a dry ash-free basis. In this case, the ash is included, and that tells you the elemental composition. So you have carbon, hydrogen, nitrogen, sulfur, oxygen here on a mass basis. And then combined with this is the higher heating value of the coal. That will be done on a dry basis. In this case, it's 12407 BTUs per pound. And the higher heating value is typically what's used, and that's the heat of combustion, which is the negative of the heat of reaction, where you assume that the water in the products exists as a liquid. So it's a higher heating value because you get more heat out when you condense the water all the way to a liquid. So that's not really done in practice, but that's what's done in referring and referencing the heating value of the coal. So here's a graphic showing some of the coal deposits in the United States, and you can see they tend to be congregated in like mountainous areas or areas that are in the plains near the mountains here. And there's some really interesting geology related to that. You also have quite a bit in the Appalachian region, and Utah has lots of coal, and you can see the different types. So red is anthracite. There's not very much red. You see a little bit here in Pennsylvania, and then you get lots of orange. That's going to be your medium and high volatile bituminous coals. You also have green subbituminous coal, lots of that in Wyoming. The so-called Powder River Basin, or PRB coal, is really common and important source. And then you have lignite, and Texas lignite, for example, is a commonly used term. And of course, the usefulness, price, and desirableness of the coal is related to its coal rank. And that's because it's going to affect things like the amount of ash, it's going to affect the heating value, it's going to affect some of the pollutants. And low sulfur coals are in demand because they produce less pollutants, for example. So it's a complicated fuel, and a lot of science goes into it. BYU's been at the forefront of coal research for a lot of years. So here's a distribution of coal power plants in the United States. And you can see here the size of the plant based on the size of the circle, and then what kind of coal it's burning, whether it's bituminous, subbituminous, or other. And so you get a lot in the West, you get a lot that's near the source of the coal because it's cheaper to transport it. And then in the East, it's all over the place, and it kind of follows. You can see the coal kind of follows where the mines are. So right through here in the middle, not quite as much, although there's also not a lot of population there. And hardly any coal plants in California, both because there isn't a lot of coal in California, and also because California has regulations that don't promote coal plants. Here's a kind of a graphic showing the United States different kinds of U.S. electric plants by start date. And so you can see the coal portion in the dark here. Lots of coal plants started in the mid-60s through maybe the mid-80s. A lot of coal plants were created, and then there was hardly any new coal plants between 1990 and 2010. You had a few that were built in 2010, but you can also see that while there were some natural gas plants created, the natural gas plants dominated at the same period of time that the coal plants kind of faded. 88% of coal capacity was installed over 30 years ago. So there aren't really any new coal generation plants being created in the United States. And that can cause some issues as they provide a lot of important base load. So some of that's being taken up by natural gas, but as the increase of renewables like wind and solar happens, some of that base load needs to be treated, and that's one of the challenges that's currently going on with power generation. In China, while the U.S. has had a significant decline in the amount of coal, China has had a major increase in the amount of coal. China is both a leader in installing renewable sources, but also a leader in installing coal-based sources. China has over 1,000 coal power plants. 184 coal power plants were under construction in 2020, just an enormous number. And in 2019, about 58% of Chinese energy came from coal. 80% of it in 2010. So China's dropped from 80% to 58% of their energy coming from coal in just 10 years. But at the same time, they've significantly increased the amount of coal plants that they've created as their energy and development has hugely increased over time. You can also see in this Wikipedia article this rise in the coal generation plants. Let's see. Coal production in China. Yeah, this thing here, where you can see this is coal production versus various countries. So you can see the United States here has dropped significantly. Coal production versus, and India's raised a little bit. Russia's kind of been flat. France and UK have dropped significantly over time, while China's just skyrocketed. Here's a typical coal-fired power plant, a schematic of what it looks like and some of the different parts. And for scale, you can see the size of a person here on the left. So these plants are absolutely enormous. And some of them are quite large. A typical unit, typical boiler here might generate 1 gigawatt of electricity, and then a typical plant might have 2 or 3 of these units. So between 1 and 4 maybe gigawatts power at a given plant with between 1 and 4 units is not uncommon. So you can see here at the beginning, the coal kind of starts on the left and ends on the right as the combustion process happens. So the coal is brought in as a solid that's chunked down to maybe marble size, gravel size pieces. It enters a pulverizer that consists of a race mill with a rotating drum, and the coal is pulverized into a fine powder, maybe 50 microns in size. And then that powder is carried by what's called primary air, and that primary air is heated. That heating helps evaporate some of the moisture that's in the coal, which will aid its combustion. When it's then injected into the furnace on the left and the right, this would be a wall-fired boiler. So you've got these burners that go through the wall, and then this green section around here is what's called a wind box, and that provides additional air to burn the fuel in the furnace. The furnace consists of water walls, so this would be a radiant section of the furnace, and so the coal flames are radiating heat to these walls, and that's going to boil water in the tubes. As the water boils in the tubes, it becomes less dense and it travels upwards, and that steam is separated in what's called a steam drum. So the liquid and the gas are separated, the liquid and the vapor water are separated in the steam drum, and then the vapor is taken off and it runs through different kinds of pendants and in these backpass heat exchangers, and those go off to the turbines. You have different platen secondary superheaters, intermediate secondary superheaters. So we talked about superheaters with the Rankine cycle, and then you also have primary superheaters. Anyway, so this is heat exchanger that extracts the heat, and you have transfer between the turbines and back to the furnace as needed in like the reheat. You can see like the reheat superheater is listed here. The temperature of the gases is decreasing as you go through the furnace, and so at the end where the gases are coolest, you have what's called the economizer, and that's going to preheat the water as a liquid before it goes into the furnace as part of the cycle. The gases pass through a SCR, selective catalytic reduction unit, to remove NO. And then it runs through another heat exchanger, this air preheater, and that's a big rotating drum that spins around. And on one side, the hot gases come through and it heats up the metal, which then spins around to the air intake side. And as the cold air passes through that hot metal, it cools the metal but absorbs heat as it's injected back into the furnace. So kind of a continuous flow heat exchanger. And there's little details involved in that, like making sure there isn't leakage in that unit, which can affect efficiency of the unit. There's fans to blow the air around. You have a primary air fan. You have a forced draft fan. The gases run through a precipitator here, which will either be an electrostatic precipitator or probably more commonly a baghouse to collect particulate. And then you have an induced draft fan to pull the gases through the unit and force them up the stack. The gases are hot, so there is a significant buoyant effect that helps draw the flow through, and that buoyancy depends on the height of the stack. But there's an induced draft fan to increase that flow rate. Then the gases also might go through, they go through absorbers for sulfur removal, and then they'll be fed into the stack where they're vented to the atmosphere. So lots of little pieces here. Make sure that you realize that a fan is not the same as a pump. We use the word fan to talk about moving gases, and we use the word pump to move liquids. So be careful of that terminology. People get that wrong all the time when they're labeling charts like this. Okay, so a couple of fun pictures of some of these burners, so-called low NOx burners. We've talked about that a little bit, how a low NOx burner, the idea is that you separate the fuel in the air in regions that it's going to burn rich, and then it's going to burn lean so that you can avoid the peak in the NOx that happens just lean of the stoichiometric point. And so there's specialized burners to try to account for that. And these burners have typically 2 or 3 air streams. You'll have primary air, which carries the coal, secondary air, tertiary air that kind of surround in an annular way the coal. And then you have these, the shape of this thing's called a quarrel. It's kind of like a little divot almost in the wall and also in the burner. And that helps shape the flame and also provides a zone that can be heated that can radiate back to the gases at the coal to try to stabilize that flame a little bit. So there's a whole science behind just the design and use of these burners. You can see in an extreme case here an example of slagging at those burners. So this would be, obviously something you'd want to avoid, and it really can foul up your unit. Then you have to shut the unit down to remove all the slag. That can be affected by how you run the unit and also by what kind of coal you're using. Here's a schematic of a steam drum on the left. These are enormous units kind of positioned at the top of the boiler. And the idea basically is a physical separation. So you have things like little cyclones, a cyclone separator, where the gases are fed through and they spin around, and that flings the liquid particles to the walls, which then drain down into the liquid side. The idea being to try to separate that wet steam water mixture with lots of little particles into effectively dry steam, so that it can be run off to the superheaters and to the and then to the turbine. And then there's these pipes here that will downflow pipes that will go back into the boiler. There's lots of different kinds of furnaces. There's the big ones that we've talked about are like wall-fired units. There's also smaller units that are called stokers, and those will typically have a grate that the coal is fed onto. These will have like gravel size chunks of coal, sometimes bigger, maybe about the size of a ping pong ball, and maybe a little bit smaller. Anyway, so they're on this grate, and the grate moves very, very slowly, and air is forced up through the grate, and it basically burns on this grate, and ash falls down into a hopper and a water trap here, which is then landfilled. This is what BYU used to have as part of their heating plant. In the summers, campus was cooled. Air conditioning was provided from the energy from a coal-fired stoker, and it was just like this. You could look inside of it, and then in the winter they used natural gas because in the winter the valleys have inversion issues and air pollution issues, so natural gas burns cleaner, so they use natural gas in the summer, or in the winter, and coal in the summer. You can burn different kinds of fuel. They're more flexible that way, less complicated and finicky, you might say, than a large-scale boiler. We talked about wall-fired units. These are so-called PC furnaces, pulverized coal furnaces, and there's different kinds. This would be a wall-fired unit, an opposed wall-fired unit where you have burners on both sides. This part of the unit is called the nose. So when we look at that, there's always this nose here that helps direct the flow. It also protects these superheaters here from some of the radiation, and has the name the nose. Kind of fun. And here is so wall-fired, opposed wall-fired, and then you have here a corner-fired unit where the coal is fed in through the corners and it makes kind of a cyclone-like device. I think that one or two of the units at the Hunter power plant in Utah are cyclone units. And there's also what are called corner-fired units, I should say. There's also what's called cyclone units. These are probably less common these days. They're a little bit older. They have a cyclone that affect a larger burner cyclone in which the coal can be fed. These can accommodate a range of fuels, everything from coal to like torn up tires, shredded tires, because they provide this cyclone where the materials can burn for a long time. They have a higher residence time, and then the gases are then fed into the furnace. And you can click the link here to see a little bit more about those. Take advantage of coal grades not suitable for pulverized coal combustion. Cyclones feed coal in a spiral manner into a combustion chamber for maximum combustion efficiency. So, some of the different types of coal burners and coal furnaces. So here's some fun videos. This is a video from the L1500. This used to be, this is a furnace. You can see the ladder here for scale. It's a 1500 kilowatt coal-fired research reactor. This was at the University of Utah in their downtown facility, and is now at the San Rafael Research Center in Orangeville, Utah. And just a video that kind of shows the operation. These, you can see what those turbulent flames look like. They're pretty impressive. Highly turbulent, highly radiating. Let's see. And here's another video. Now you're going to see the figure change quite a lot. That changes because of the sensitivity of the camera. It's not the film. But you can also see kind of the coal dust almost coming through, and these hot streaks. Yeah, the so-called roping, where you get different chunks of powdered coal gases. Who doesn't love flames and fires, right? And then finally, some images of coal particles burning. And you can see in some of this how, if you look carefully, you can see some of the structure of the coal gases in the flames. Okay, so if you have questions, drop a comment or shoot me an email.